Our paper today has to do with the alignment problem, which can be succinctly summarized as how can we get AI systems to act in accordance with our values? And this idea has been around as a problem and articulated since at least the 1960s by Norbert Wiener, who famously said, as machines learn, they may develop unforeseen strategies at rates that baffle their programmers. In addition to this question of how do we get AI systems to act in accordance with their values, another question is what should those values even be? And so our paper today tries to examine both of these questions. So in particular, current approaches are often focused on specific model families, say, for example, large language models, or even specific features within particular models. So for example, mechanistic interpretability is often focused on, say, one type of model, like a Claude Opus model, or an OpenAI model, or an open source model, like a Qwen model. But oftentimes it's not clear what will end up transferring as we change the model architecture or the data set or even the learning hyperparameters, keeping those other two things fixed. Furthermore, AI training has grown in complexity. So RLHF in 2019 was a much simpler data pipeline, but nowadays, especially with state-of-the-art models, requires very complex chaining of different data sets that are then evaluated empirically in red teaming. And so as a result, we hardly have any theoretical guarantees about alignment, except in particular settings with very strong assumptions that don't necessarily hold in practice. Instead, our approach is to try to study the intrinsic complexity of alignment itself by abstracting away from these details, but keeping the core principles intact within a very general framework. And what this allows us to do is to identify hardnesses, so no-goes and complexity barriers that occur even in the best case settings where we can prove alignment. And this then allows us to suggest practical strategies that avoid these barriers. So our framework in particular is known as MN epsilon delta agreement, and it starts by specifying M objective functions. These are more generally simply bounded functions. But just to give an example, as I've shown here, we can kind of think of them as for example, the RLHF objectives that we want our AI agents to have of helpfulness, harmlessness, honesty, refusal of bad things, as well as preserving user privacy. And for each of these objectives, we have N rational agents. We can kind of think of these as akin to either being human raters or AI agents that each have their own private knowledge that they're then trying to communicate by exchanging messages. So we can think of these messages as the scalar judgment tokens that we use in RLHF to specify our pairwise preferences until they reach epsilon delta agreement. So until they basically agree on their expectations for this reward function within some epsilon that is user set with high probability, with probably at least 1 minus delta. And we can kind of think of this very relaxed notion of probabilistic approximate agreement as modeling preference aggregation convergence on a per task state space, each of which for each of these M tasks being of size D. And what we show are two main results. One is that no free lunch theorem, that aligning to all human values is not tractable, even for computationally unbounded agents. And instead, we should pick small objective sets to align over. And the second is that reward hacking is inevitable in large state spaces and bounded agents. So even if we can prove alignment, because of resource constraints, we don't always get that alignment as being tractable. And instead, what we should do is select important parts of the state space along with mechanism design, which I'll touch on at the end. So one of the reasons our framework is general is that it encompasses prior both Amen agreement literature from game theory, as well as prior alignment approaches such as AI safety via debate, iterated amplification, as well as cooperative inverse learning, inverse reinforcement learning, or SERL. And our operating principle by encompassing these other approaches is that basically if something's already inefficient in our kind of theoretically ideal setting of unbounded Bayes rational and cooperative agents, where we can prove alignment, then we should just avoid it in practice. And what I'm going to show today is that we run into a couple of fundamental inefficiencies here. So in particular, just to start with the first thing of the no free lunch theorem, what we show is that there exist functions, input sets, and prior distributions such that any communication protocol across all possible communication protocols among n agents needs to exchange at least mn squared log 1 over epsilon bits to achieve this alignment. So what this is saying, in other words, is that if we have a large number of tasks M or agents N, then it's going to be intractable to align them efficiently, even if the agents themselves are computationally unbounded. Even if constructing the messages is constant time, that they can sample as much as they need, there's no computational restrictions, you still have this overhead. And so what this suggests is that we should choose our tasks and agents wisely since we have no free lunch. So for example, if we had one objective that we need to agree on per state, that would even be bad because the number of states, D, could be exponentially large. And next question we can ask is, rather than trying to come up with a universal lower bound across all possible ways agents can communicate, can we improve this by considering natural but still broad classes of protocols? And this is what connects to the second result of reward hacking being globally inevitable, which is that if we think of natural ways in which agents can communicate, we can show this additional dependence on the task state space size D. And in particular, the assumption that we're making here is that one, the messages that the agents are setting are bounded, and two, that they're communicating finite numbers of bits to each other. So these are very general, natural assumptions. And then finally, that the state spaces are connected so that we can basically converge. And this builds on prior work from the game theorists Ziv Hellman and Dov Samit. And what we can show is this additional dependent on a task state space. So not just M and N, but also the size of the state space itself. Now, we can additionally look at not just computationally unbounded agents, but bounded agents. So now messages don't just take constant time, they might have noise in them. And furthermore, the agents sample each other's likelihoods. So you can kind of think of this as the process that's akin to sampling from a large language model, right? When we prompt a large language model, we get back an output. That's exactly what they're doing here, is this type of sampling. And we can also have differential querying. So if one of the agents is a human, we can actually show that we can study how different subroutine times between querying them can be much more costly or inefficient in this setting. And the kind of TLDR here is that we can get an exponential slowdown in the task state space size T. So no longer just a linear dependence, which is already bad, but a further exponential dependence on that. And so in particular, on the left in theorem 2, we can show an algorithm that demonstrates that it can converge. That's not some impossible problem, but that this can take exponential time in the state space. And on the right, in proposition 5, we can show that for rare events, we can show that we can do no better, actually, than this kind of exponential dependence on D across all possible bounded functions. And so as a result, this connects to reward hacking because we're showing that this result holds across all natural communication protocols across all bounded functions, not just any particular function. So our takeaway so far is that alignment itself is fundamentally constrained by three quantities: the number of tasks, M, the number of overseers, N, and the state space size, D. How might we avoid some of these barriers? Well, from the first no free lunch barrier, which had to do with the number of tasks and agents, we think compressing your objectives is a good idea. So in other words, identify a small set of context-dependent values per setting. So for example, in a coding agent, you might imagine that you can agree on, well, the code needs to be functional, and it needs to be well documented. So it just needs, and pass unit tests. So it needs only a few criteria to specify a few objectives. Or what you can do across all agents is kind of pick a neutrally universal target that leads to small value sets. So one of those, which will be appearing in the machine ethics workshop on Tuesday, is known as corrigibility, so avoiding loss of human control. And we can show that about 5 objectives is enough to prove guarantees there. And the other aspect connected to the reward hacking is to compress your state space. So in particular, now that we know that there aren't any globally unhackable reward functions if our resources are constrained, then instead what we should do is exploit task structure and focus on safety critical slices rather than uniform coverage. So this could come about through stress testing the agent and post-training with multi-turn interactions rather than one shot that's done in RLHF. And I think there's lots to explore there. With that, there's a lot more details in the paper, which I've linked above, as well as a LessWrong summary on the top right. And I've also linked the second paper that's a positive construction for corrigibility as well, which will be appearing in that workshop. Thank you so much for your time.